So this is the movie for section 2.3, and our objectives in this section are going to be to find the exact values of the trig functions of pi over 4, which is equal to 45 degrees. But I'm going to encourage you to start thinking in radians. So pi over 4 radians, which is the same as 45 degrees. Then we're also going to find the exact values of the trig functions of pi over 6, which is equal to 30 degrees, and pi over 3, which is equal to 60 degrees. So these three are called the special angles because they come up a lot in lots of application problems. The third objective is going to be to use a calculator. So you will need your calculator to approximate. So when we use a calculator for other angles, we're getting approximate values. So you use a calculator to approximate the values of the trig functions of acute angles. So this is of other acute angles, not these special ones. And the fourth objective is going to be model and to solve applied problems. And in this section, it's going to be involving right triangles, because those come up a lot, because as soon as you have horizontal and vertical, you have right triangles being formed. So the first objective is going to be find the exact values of the trig functions of pi over 4 radians or 45 degrees. So here's a right triangle. We have the little box in the corner, 45 degrees. Well, remember the angles have to all add up to 180 degrees. So if one of them is 90, the other two have to add up to 90. And if one of those is 45, clearly the other one has to be 45. So this is called an isosceles triangle. Iso prefix meaning same. So it has two sides the same length and two angles that are the same size. So we know that side A and side B are the same length. So the side lengths of A and B are equal. And without loss of generality, and that means it doesn't mean if we use A or B if they're the same. So the Pythagorean theorem, which would say a squared plus b squared equals c squared, becomes a squared plus a squared equals c squared. So 2a squared equals c squared. So suppose we let a equal b equal 1, then we get the very simplest version of this triangle. So if a is 1, then c squared equals 2. So c equals plus or minus root 2, but this is a triangle, so we don't need the negative. So if the side lengths of the shorter sides are each 1, then the hypotenuse is the square root of 2. Well, because we're concerned with ratios and not the actual side lengths, we can now compute the values of all the trig functions of the angle that has the size of 45 degrees or pi over 4 radians. You must memorize these. So the sine of pi over 4 or 45 degrees is, remember, the opposite over the hypotenuse, so 1 over root 2, and if you rationalize the denominator, then you'll get root 2 over 2. So either 1 over root 2 or root 2 over 2, I don't care which one. And then we know the cosecant is the reciprocal, so it must be root 2. And then this is an interesting characteristic of the 45 degree angle. The cosine, the adjacent over the hypotenuse, is exactly the same number as the sine. So this is the only angle that has the sine and the cosine equal. It's a property of the angle or a characteristic of the angle. And again, we know that the reciprocal of cosine is secant. So if the cosine is 1 over root 2, the secant must be root 2. And then the tangent, this is interesting, opposite over adjacent, 1 over 1. So the tangent of an angle that has the size of 45 degrees, regardless of the triangle it's in, has a tangent of 1 which means its cotangent must also be 1, since the reciprocal of 1 is 1. So you need to memorize these values. They're really important. Objective 2 is going to be to find the exact values of the trigonometric functions of pi over 6, which is 30 degrees, and pi over 3, which is 60 degrees. So we're going to start with this triangle below, and then we're going to create an equilateral triangle. So we're going to make 3 60-degree angles by making another 30-degree angle here at the top and a 60-degree angle here in the right corner. And that means if this side length is 2, the base of the triangle now has to have length 2, because we created an equilateral triangle. All the side lengths are equal, all the angles are equal. So if the base of the big triangle is 2, then that must mean A equals 1. So we can figure out the height by the Pythagorean theorem. So we have 1 squared plus b squared equals 2 squared. So b squared must equal 3, and b equals plus or minus root 3. But again, we're in a real triangle, so b must be square root of 3. So I'm showing you this so you can remember where these values come from and that we didn't just make them up. So the simplest version of a similar triangle with all the same values for its trigonometric functions would be with the base 1, the hypotenuse is 2, and then the height would be root 3. So the sine of pi over 6, the 30-degree angle, the sine is opposite over hypotenuse, so 1/2. So we know the cosecant, which is the reciprocal, must be 2. Then we're looking at the 30-degree angle. So the adjacent over the hypotenuse is root 3 over 2. So that means the secant is 2 over root 3. Or if you want to rationalize the denominator, you're going to get 2 root 3 over 3. Then the tangent of pi over 6 is opposite over adjacent. So 1 over root 3, or if you rationalize the denominator, root 3 over 3. And then the cotangent is the reciprocal, root 3. So then let's notice something that also comes from the complementary angle theorem, that the sine of pi over 3 must be the same as the cosine of pi over 6, and you can see that really clearly in this triangle. So now we're focusing on the 60-degree angle. So let me erase this on the 30-degree angle. So the pi over 3 angle, if we're looking at the sine, is the opposite over the hypotenuse. Well, now we see that's the one that's root 3 over 2. So the cosecant must be 2 root 3 over 3. So these are the co-functions are equal. Remember, secant and cosecant are co-functions of complementary angles are equal. And then we see that the cosine of pi over 3 is 1/2, so the secant is 2, and the tangent of pi over 3 is root 3, so the cotangent is 1 over root 3, which is the same number as root 3 over 3 if you want to rationalize the denominators. So you've got to memorize all the values of the trig functions for these 3 angles. So here they are in a nice little chart if that helps you with memorizing. So now we're going to use a calculator to approximate the values of the trig functions only of acute angles right now. We'll get carried away and do every kind of angle eventually, but we start with the acute angles that live in a right triangle. So look at your calculator, your scientific calculator, and the only functions you can calculate with the press of a single button are sine. So you should see a button that says SIN on your calculator. Cosine, the button will say COS. And tangent, the button says TAN. The other 3 functions we have to find by knowing that they're reciprocals. That's saved buttons on the calculator. So we'll do these exercises in class together, so make sure and bring your calculator. So number 4 is model and solve applied problems involving right triangles. And these are very challenging, so we are going to spend some time in class working on them. And make sure you make a note of this box, and I actually have a post-it note on this page in my notes because I keep forgetting it. And it's very important because my math lab is very particular about this. In the rest of this course, angles are measured to the nearest tenth of a degree, and side lengths are measured to the nearest hundredth. So we'll talk more about this in class, but really important concepts in trigonometry. An angle of elevation, if you're a little person standing here, and there's a big cliff here, and you're looking up at it, this angle is called the angle of elevation. What's the angle you would have to tilt your head through to be able to look at the top of the cliff. And then the angle of depression would be, what if you were standing at the top of a cliff and looking down, then we'd have the angle of depression. How much of an angle would you have to rotate your head through to be able to see down to the ground? So notice that we're always referring to the horizontal. We're always saying, how far are you off from horizontal? How far did you have to look up to see the top of something? Or how far did you look down to see something that was below where you were? So let's look at an example problem, and we'll work on this some in class. But I want you to start thinking about it, where it's talking about a tower in Toronto, Canada. It was the tallest structure in the world at the time of the printing of this book. So I would just draw it as a really tall stick. So this is the CN Tower. So while visiting Toronto, a tourist wondered what the height of the tower was above the top of the sky pod. So there's a little sky pod right here. So they're wondering, what's this distance right here from the sky pod to the top of the tower? So they first measured their distance away from the bottom of the tower, and that was 4,000 feet, and then measured the angle to the top of the sky pod to be 20.1 degrees. And standing at the same spot, the angle of elevation to the top of the tower was found to be 24.4 degrees. So we'll use this information during class to see if we can figure out this number, that's the distance between the sky pod to the very top of the tower, using trigonometric functions. So that's all for this section.